Alright everyone, welcome to another Physics QBits video. In this QBit, we're going to talk about some of the conceptual ideas and some of my practical kind of problem-solving tips when it comes to working through problems that involve uniform circular motion and centripetal force. Okay. And so let's hop right in with a quick introduction about what centripetal force actually is. So the situation I like to start with for teaching centripetal force is imagine you're driving on a circular racetrack at a specific speed of 60 miles an hour, okay? And my first question for you is, which direction does the acceleration have to be in? We know that there has to be an acceleration because if I look at a car later on the track, right, my velocity direction is going to be different. And so because the velocity direction is changing, that means we have to have some acceleration. So I'll give you a few seconds to think about this question, and you can pause if you want some more time, and then we'll kind of talk about it together. Okay, in order to answer this question, we need to recognize two key facts. First of all, the speed is constant, and the direction is changing. Okay, this first fact tells us that we definitely know that the acceleration can't have any components in the direction of v, because if that were the case, right, if the acceleration is at all pointed near the direction of v, then the object is going to either be accelerating or slowing down. We can also use the fact that the direction is changing to tell us that a is definitely not equal to 0, right? Because we know that there must be some acceleration if the direction of the velocity changes. And so combining these ideas together, the only solution to this question is that we know that the acceleration must be exactly perpendicular to the velocity. In other words, if we indicate this on the diagram, we have some acceleration pointed inwards towards the circle that causes the object's direction to continuously change, but causes the speed to be the same the whole time, okay? And so one thing I like to call this acceleration is just a steering acceleration, to remind ourselves of the idea that this acceleration only changes the direction of the car and does not at all change the speed, right? And so this acceleration, by the way, the one that points inwards towards the circle, this is what physicists call the centripetal acceleration. And like we just talked about, the real purpose of this acceleration is really just to redirect the cart. It's just to steer the cart, not to change the speed of the car, okay? And the second question we might have about this acceleration is, what is the actual magnitude, right? How strong is this acceleration? And so what I want to point out when you think about this question is the following. If we're doing this on a racetrack at a particular speed of 60 miles an hour, right, we can't just pick kind of any old random angle to turn our steering wheel in order to travel along this track. If I want to drive on this specific racetrack at 60 miles an hour, there is one single angle that I can turn the steering wheel in order to stay on the track, right? If I pick the wrong angle, eventually I'll kind of drive off the road. And so that means there's only one possible value of A, and we'll call it AC for centripetal acceleration, right? And so if you buy that argument, I'm going to skip the derivation for this, but it turns out if you insist that you're driving in a circle of radius r at some velocity v, the only possible value of acceleration that will keep you on this track is v squared over r. If we think about this as a force, right, we know that there's going to be some combination of like forces that allow us to have this turning, this steering ability. We can compute the centripetal force associated with this acceleration as just m times AC by Newton's second law, or if we fully write it out, mv squared over r, okay? And so I wouldn't worry too much about where these equations come from, but the key fact that I want you to remember here is that when someone tells you that an object is traveling in a circle at some radius r with some velocity v, the acceleration and the force have to be these values, because if they aren't, right, then you've picked the kind of wrong angle for the steering wheel to be at, and you're not actually going in the circle that you've told me you're going in, okay? And so the key idea here is that when we think about problems with uniform circular motion, we want to think about uniform circular motion as a constraint, okay? Driving in a circle at a specific velocity or a specific speed is a very, very specific motion, okay? And so what that means is we need to treat UCM, gosh, my handwriting is terrible today. We need to treat UCM as any other constraint. Okay, so what I mean is there's other constraints we've run into in physics, right? One of them is talking about an object that remains at rest. We know that if the problem specifies to us that an object is remaining at rest, we can immediately write down a couple facts that we know. First of all, that means the net force on the object has to be 0, right? And we also know that the net acceleration of that object also has to be 0, right? These are mathematical statements that kind of quantify this constraint that the object remains at rest. Similarly, if a problem tells you that something is undergoing UCM, in other words, driving in a circle of radius r at some speed v, where notably have not had the vector error, right? This is just the magnitude. We immediately know that there's only one value of the acceleration and one value of the force that will get you this specific trajectory. And that is the total force has to be Fc, where Fc is our centripetal force, right? And it has to be exactly mv squared over r. If the force is not exactly this value, then the person who gave you the problem lied and your object is not actually going in the circle, okay? Similarly, then we know the net acceleration has to just be the steering acceleration AC, which is just v squared over r, okay? And notably, this is only true if the object is at constant velocity, or constant speed, I should say. If the speed is changing, then something slightly different happens, and we can talk about that in a later video. But for now, we'll just assume that everything is really going uniformly, okay? The key point is that you want to think about UCM exactly the same as you think about remains at rest in a physics problem. They're giving you secret information in terms of an English sentence, right? But we can translate that information into some mathematical constraints on the value of the net force. In the case of at rest, that net force is 0. In the case of UCM, that force is mv squared over r, okay? And so another question we might have to answer is what objects can apply centripetal forces, right? We know that like ropes apply tensions. We know that normal force gets applied by a surface, right? We know that hands give you applied forces. And so our question is, what things provide centripetal force? And the answer turns out to be anything that provides any force, okay? Remember, centripetal force isn't a special force like tension or normal force. It's a condition that must be fulfilled by other forces in the problem, okay? So UCM is a constraint that can be fulfilled by any combination of forces. And so, for example, let's look at a problem where we have a ball on a string, okay? And let's assume this whole thing is in space and there's no gravity, no friction, and none of the other annoying things that teacher likes to put into our physics problems, okay? What I can do is draw a free body diagram for this object, and I'm going to draw it from the kind of top view. So I'll draw my dotted circle for the trajectory, and let's look at what the object is experiencing when it's on this side of the circle here. We can see that there's only one thing touching this ball, right? It's just the tension, and there's no other contact forces, and there's no non-contact forces. So our free body diagram just has a tension pointing inwards, okay? In this case, the way that we want to think about this is we've been told this object is undergoing UCM at some velocity v in some circle of radius r, okay? So that means we know necessarily the net force has to be exactly mv squared over r towards the center. This is the exact value of the net force that will cause this object to go in specifically this circle, okay? And so when we look at our free body diagram, what we can tell is the only force that could possibly be providing this constraint is the tension, right? And so that means we can immediately claim that the tension is exactly equal to mv squared over r in magnitude, right? If it's not exactly this value, then we violated our uniform circular motion constraint, and now this is no longer like actually going in a circle, okay? I know I'm hitting that point really hard, but I think it's really, really important to remember. And so one other thing that can happen is sometimes multiple forces, right, can provide the steering centripetal acceleration. And so let's imagine instead we're on a loop-de-loop coaster, okay, and there's no friction, but now there is gravity. And we can draw the free body diagram again for this guy here, right? And we can recognize now, well, there's a gravitational force pointing downwards of just m times g, okay? But now because our butt cheeks are firmly planted on the seat of the roller coaster, we know there's going to be an additional normal force of some unknown value Fn, okay? And so once again, because we know that we're in a circular track, right? We're going kind of along this circular loop at some velocity v, at some radius r, the laws of uniform circular motion dictate that whatever the net force, whatever things are providing the net force, we know they have to add up to exactly mv squared over r towards the center. Okay? And in this case, when we inspect our free body diagram, we can tell that our net force is minus mg, because we have our usual kind of axes here, right? Minus Fn. And because of uniform circular motion, we know that these two have to add up to have a value of mv squared over r with the negative sign, because now towards the circle, right, is downwards, okay? And so now, right, the idea is whatever forces are here in the free body diagram, those are the candidates for things that could provide the centripetal force, right? But all we know is that when they combine, they had better add up to mv squared over r, because that's what the problem told us needs to be the case. And so if I wanted to solve for the normal force in this instance, for example, I could find Fn is equal to mv squared over r minus mg, okay? And so this way I can use my constraint to solve for any forces that I don't know in this situation. The last thing I want to do is just kind of run through a full UCM problem just to show you all what it looks like when we try to do these problems with our kind of full four-step force problem procedure, okay? And so imagine that now we have someone on a skateboard or rollerblades, it doesn't matter, on like a half pipe, okay? So they're on this kind of like bottom part of the circle, and at the bottom of their trajectory, they're going to the right at some velocity v. We have some mass m in total, and the radius of curvature of the half pipe is this capital R, okay? The question is, what is the normal force between the skateboard and the ground that's helping kind of steer our skateboarder along the trajectory of the half pipe? And we'll assume that this object, or all the objects here are frictionless, so we just have our kind of, our easy forces, I'll say. And so when you're doing these UCM problems, my advice for you is the easiest way to do this is treat this problem like a regular force problem, and then wait until after you write down your Newton's second law equations to substitute this condition that F net must be mv squared over r, okay? So let's go through our kind of usual four-step process, starting with the free body diagram, then writing down the associated Newton's second law equations, and then applying our constraints, and solving for any unknowns. And let's do this for this problem, and then at step 3, we'll kind of think about the UCM part, okay? So step 1, for the free body diagram, what we're going to do is draw our dot, and we can see that the things that are touching our skateboard plus skater system are the ground, right? So we know that we have some normal force pointed upwards, and there's nothing else touching our skater plus skateboard system. And so the only other force in this situation must be non-contact forces. And in this case, that's just going to be Fg equals mg downwards. And I'll draw my little kind of orientating y-axis conventions for positive and negative here. And so because there's only one contact and one non-contact force, then our free body diagram should be complete here, okay? So now what we have to do is use this free body diagram to translate into some Newton's second law equations. Fortunately, there's only forces in the y direction here, so we only have our one y direction Newton's second law, which tells us that F net in the y direction must be the sum of all the forces, in this case, plus Fn, okay, minus mg, since Fn points up and mg points downwards, okay? And so this is our one equation that we need for this system, and this must be equal to ma by Newton's second law, okay? And we'll even say may. And so now, after our after our Newton's second law equations, now we want to think about our uniform circular motion constraint. Okay, so because this object is undergoing UCM, right, like we said before, that means we know something about the net force. We know the net force has to be mv squared over r. And the other question we need to answer is whether this is positive or negative, okay? And so if I take a look at my diagram, we know that the laws of UCM tell us that the centripetal force must point towards the center, right? So the net force in this case has to be positive because that's the direction the acceleration needs to be in order to kind of continue steering our little guy on the half pipe. And so now, just like any other constraint, right, if we knew the system was at rest, we could plug in a equals 0, right? But because we know this is at UCM, we can plug in that we know the value of the net force must be mv squared over r. And so what I can do is substitute that I know the left-hand side of this equation, this F net part that I'm underlining here, has to be positive mv squared over r, and the right-hand side still remains Fn minus mg, right? And so this equation is telling us that whatever Fn and mg are, the total combination of them has to be exactly mv squared over r, once again to make sure that our skater is maintaining their circular trajectory, okay? And so finally, we can try solving this for the normal force, and we find that Fn equals mg plus mv squared over r after adding mg to both sides. So let's add mg plus mg, something like this, right? And so in this case, what we find is that even though there's two forces, okay, the normal force is the one that's pointed in the direction that the steering acceleration has to be, right? And so in this case, what we find is Fn has two jobs. First, it counteracts mg, so it makes sure that the skater does not kind of fall through the bottom of the half pipe. I'll slide this over and make this a little nicer looking. Oops. Counters mg. Good. And the second job of the normal force is to provide mv squared over r to make sure that the object in question is still on our circular trajectory, okay? And that's why it makes sense that this normal force ends up being mg plus mv squared over r, right? It has to beat gravity, and on top of beating gravity, it has to also steer our skater, okay? And so the thing I want to highlight here is that when you're doing this problem, right, we can do steps 1 and 2 as usual and not think too hard. And the place we really want to be careful is in this constraint step, where we plug in the idea that we know that because this object is undergoing UCM, we know what the net force has to be, okay? All right, so with that example problem done, I just wanted to kind of leave you all with a summary as per usual. And so remember, all of our work in this video has centered around systems where we have an object traveling in a circle of some radius r with some mass m at some velocity v, right? And it turns out that going in a circle, or in other words UCM, is a very constrained motion. And by constrained, I just mean it's a very specific motion, right? Think about, once again, like you can only turn your steering wheel in a particular angle. You can't just pick a random angle. And what that means is that we have to satisfy a particular constraint for the net force in this system. If the acceleration is not exactly v squared over r in total, or identically, if the net force is not exactly mv squared over r, then your object is not actually going through uniform circular motion, okay? So these are the constraints for UCM. And so when you're solving problems involving UCM, I'll encourage you to kind of do steps 1 and 2, where you draw the free body diagram and Newton's second law equations as per usual, and then delay thinking about these constraints until step 3. So when solving UCM problems, do FBD plus Newton's second law equations as usual. Wait until step 3, constraints to apply. F net must be definitionally mv squared over r, or equivalently AC equals v squared over r. Either one of these will work depending on kind of whether you want to think about forces or not, right? But the point is, these are really constraints that you can apply exactly the same as if you knew a system was at rest, so that the net force and the net acceleration must be 0, right? We want to treat these the same way. Okay, that's really all the advice I have for you. If you want to see some more complicated uniform circular motion problems worked out, then you can check out the office hours video that I'll be releasing later this week, where we go through kind of some more complicated setups and some kind of goofy, maybe unrecognizable UCM problems. But for now, this is all I have for you. As per usual, thanks for stopping by, and if you have any thoughts or questions, you can leave them in the comment section below, and I'll try to get to them. And finally, please don't forget to like and subscribe for more free physics problem-solving tips and tricks. This has been Physics Tutoring Quantized.